So yeah, today I'm going to be presenting kind of an update of some of the experimentation and results that I've been working on this summer. So as we've kind of talked about before, the purpose of my work this summer is to be investigating the effects of the chemical structure of the polymer precursors and also the pyrolysis temperature on the evolution of carbon within polymer-derived ceramics. So again, we're going to start with that siloxane precursor. So I have 3 different polysiloxanes, and then I am pyrolyzing each of them at 3 different temperatures, which is 800, 1000, and 1200 degrees Celsius. And then from that, I'll get 9 different samples. And in addition, I've also cross-linked all of these in argon, and then this week I'm going to be cross-linking all of them in air. So I'm actually going to have 18 different samples that I'm going to be working with and kind of doing some spectroscopy on in the future. So to kind of just start out with some general information of why we're using siloxanes. Siloxanes are examples of precursors that are very important to industry when they turn into their ceramics. So generally they are very thermally stable. And also, as I'm kind of helping Shakir with some of his work for his PhD, he wanted to be studying materials that are spinnable. So siloxanes are going to be spinnable when they are cross-linked and such. And then as for the specific siloxanes that I'm looking at, these are kind of the short names for them. I have the long names on the next slide. These have not really been studied very much, so that's kind of why I'm looking into them. And then they have phenyl and methyl groups that are going to be necessary for the polymerization that we're going to need to be moving forward with the ceramization process. So these are the longer names for those precursors that I'm working with. So this is going to be the TPTS, the structure for it. You can see right here. The second one here is DTDS, which is right here. And then the last one here, very long names, is DDTS, and that is going to be over here. So you can see all of them have those like methyl groups on the sides, and you can see the different structures of all of them down here in these images. I'm not going to try to explain them because I have not really had too much time to look into what all of this notation and everything means, but that will be hopefully better understood by me in the next week or so. So here are some of the results I've gotten. So from cross-linking in argon, the TPTS has given about 72% yield. The DTDS, I lost a lot of mass with this every time I've tried to cross-link it. So it's given about 25% yield. And then the DDTS actually has a pretty high yield from cross-linking, which is going to be around 93%. And then the cross-linking temperature ranged from 180 to 200 degrees Celsius. Again, I did this in a glove box, which had argon. And then from pyrolysis in argon, I've had a lot of issues with my yield from pyrolysis. So what I'm actually doing right now is I just cross-linked all of these same samples in air in hope that when I pyrolyze them, they will give a much higher yield. But you can see that all of the yields here, especially with my DTDS, have been very low. So we're kind of trying to troubleshoot that right now and kind of figure out the issues. And hopefully by next week, I will have some better looking yields from my new samples. And then on Wednesday, I was able to go to KU to look at some Raman Spectroscopy and also FTIR. This is very preliminary data. I haven't gotten the chance to do any curve fitting or anything, but this is just what I plotted in Origin with my DTDS data. So you can see that as the pyrolysis temperature is increasing, this kind of is going up. The intensities, well, of these sections are going up. You can see the D and the G bands. So as of right now, this is kind of looking like what I was hoping it would look like. So that's exciting. And this is also the information for the DDTS. On Wednesday, I had only had one sample, so this is just what I have from that. You can see very sharp bands here. The intensity wasn't really high on any of the samples that I did. So this is what I have for Raman so far. And again, that is used to identify the composition of the carbon. So the D band is representing that kind of disordered carbon structure, and then the G band is representing the more ordered structure. And then for FTIR, I was also able to do that on Wednesday at KU. I haven't had a chance to plot any of that, even kind of like preliminarily, so I don't have anything to show for that yet. But this was used to identify chemical bonding between components and kind of to determine the presence of the silicon, because we couldn't see that in the Raman spectroscopy. And for all of my samples that I did FTIR with, we did see silicon oxygen and silicon carbon bands or bonds, sorry, which is good because I'm working with SiOC polymers. So yeah, that is all that I have for this week's presentation.
Okay, thank you, Mabel.